Hello everyone, welcome to Protective Relay Applications, the practical approach to relay testing. I will be your presenter today. My name is Cameron Grass. I'm an Engineer 2 of the Substation Protection and Control Group here at Power Engineers. I also have 3 years of testing and commissioning experience through a previous company, and I'm also a grad of the EET group at UMaine, class of 2019. If anyone has any questions or comments regarding any of these presentations that I will be giving out to you guys, please feel free to reach out using either my email or the phone number attached on the presentation. So with the next 3 presentations, we're going to go over some of the fundamentals of the power testing and energization group, some of the things that we do out in the field, such as relay testing, apparatus testing, functional testing, and field to verify. Pretty much just going over the basics of each of these sections and what it takes to get the job done out in the field. So the outline for this course specifically will cover the planning of the work, isolation, identifying the equipment, preparation and setup of the testing itself, returning the equipment to service, and verifying equipment in service. We'll also be going over some HPI topics and safety topics as well. HPI stands for Human Performance Initiative, which is extremely important out in the field, and you'll see why. So first section, we're going to be talking about the outage planning and the one-line prints, reading them, understanding them, as well as identifying roles and responsibilities, interpreting the scope of work, identifying the outage parameters, and identifying the equipment need to be tested. To get started, a brief explanation of the major roles and responsibilities of the testing engineers in the field. The field guys are usually the last leg of support for necessary design changes. If we get a print out in the field that has incorrect functional verification, it just doesn't work, or it actually doesn't even exist out in the field, such as equipment that was never ordered, isn't fit to the right specs, or just doesn't work at all. We're usually the last leg for any design changes, reaching out to the engineers that put the design package together and getting their support on what the next steps would be. Like I said, we verify the equipment is installed properly. We work alongside electricians to verify this. We go through each and every circuit, each and every piece of equipment that gets installed, test it, functionally test it, and then put it into service at the end. We also communicate to the client very frequently. We report any changes, issues we may be having, design changes themselves they like to know. Everything that is important to them, we try to communicate to the best of our abilities. They like to know what's going on and make sure that their money's going to the right people for making sure the job gets done well. A lot of our responsibilities, specifically verifying the equipment functions per design intent. This very easily is explained, meaning the equipment that we see on the prints that we get handed to by the engineers, we understand how it works, we test it, verify that it works per their design intent, and we can verify it that it will work properly once the equipment is in service. Testing all the equipment, all the circuits, everything, and marking up the prints is extremely important. This shows that if something does go wrong or something needs to be changed on the prints, we mark it up, make a note of it, and then those will be sent back to the design engineers at the end of the project for them to pretty much redraw whatever we mark up and submit those to the client as what we call as-builts, which are pretty much the final design of the print that shows what equipment is in service and how it should look if someone were to go out on site and utilize those prints. We also, the last thing especially, we record data whenever necessary. The CYA stands for Cover Your Ass. This is extremely important because when working with clients, they like to know what's going on, as said previously, but it also helps that you have documentation to support everything that's going on. This helps especially when they question something that you may have done, say, why did you do that? What was the issue with it to begin with? You have documentation, prints, whatever. Pictures are really useful as well to show that what you did was either correct or incorrect depending on the circumstances. So we're going to go through a quick little scope of work project. We're going to be identifying the equipment that needs to be installed and removed, checking our zones through the one lines, reviewing outage and energization plan, and understanding time constraints for troubleshooting. So this is a relay one line. You guys have probably seen quite a few of these based on the previous presentations from other groups, but in a sense, what we utilize out in the field is to get a very good understanding for the relay testing purposes, identifying the zones of protection depending on which relays you're going to be testing and where they should end up on the physical one-line layout. So we're going to go over the zones of protection for this specific section of lines. We are going to be identifying the zones of protection for the Boston line relay. So the first section is going to be our line protection zone. Those relays, the primary and backup, should be covering anything that's on the line going out to Boston, any breakers, CCVTs, anything like that, any major equipment that should be looked at. The breaker itself off to the left, the BL2 breaker, is going to be our main source of protecting the line in case of a fault. That line relay is going to operate the breaker depending on the fault scenario on any of the incoming line currents or voltages. On the left side, going out to the other piece of the yard, is going to be our bus protection. That's going to be utilized by a primary and backup relay that should cover all zones inside the yard of that breaker, meaning that if there is a fault that occurs somewhere on the Boston line, that relay is not going to operate the breaker to mitigate the fault. That's what our line protection is for. And you can see where the overlap occurs for both sides of the protection. The bus protection actually goes to the right side of the breaker, and the line actually goes to the left. This is done so that you're covering as much of the zone as possible, and you can also see that the primary and backup will be overlapping on the CTs on the left and the right there. We're going to identify the relays in our scope. Those will be our line relays down there. We're gonna assume that they're gonna be replaced, and it'll be our job to take care of the isolation and restoration of the relay circuits, testing the relays themselves, and identifying them to be the correct per the design intent. And lastly, on this little string, we're going to identify the lockout relay that may be associated with the relay replacement job. A lockout relay is pretty much a device that takes in contacts from any correlating equipment, specifically the relays, for example, and operates multiple breakers all at once to cover for a worst case scenario type event, if you would. They're very, 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 very they're utilized very frequently. They're extremely important, and they can be super beneficial to mitigating like a worst case scenario outage. On the opposite side of it, testing them can be quite dangerous, especially if you are testing something that runs to that lockout that also covers stuff that is in service equipment, meaning you could have an operation occur when doing your testing on the new equipment and accidentally open up a breaker that is in service, causing an outage and making the client very unhappy. So we're going to be going over the drawing equipment, the 1 lines and 3 lines drawing review, finding out what zones of protection will be utilized and what relays will be associated with them, and apply a basic understanding of the relay functions for, specifically in this case, the 411L and the 451. The 411L is commonly a line protective relay. It's a single-ended protection that can communicate based on tripping, and also offers reclose initiate and breaker failure initiate, which is what the RI and BFI stand for. Reclose initiate is extremely beneficial in some cases where if there's a quick little fault on the line that may self-mitigate, or you get a bad reading for a millisecond on the line, it can open and close the breaker in an instant without losing too many customers, in a sense. The breaker failure initiate is the same idea when we talked about the lockout relay previously. Pretty much is the worst case scenario tripping function that triggers a lockout to open up all the necessary equipment. The 451 is most commonly used for breaker control specifically. It covers most of the equipment that surrounds a breaker itself, offers some of the same protective functions such as the breaker failure, reclosing, and also offers supervisory control and alarms to SCADA, which could be utilized to let dispatch know, the dispatch on the client's end, that the breaker failed or there was a fault that occurred somewhere in the yard. Just a couple examples here. On the leftmost drawing is what we call a 3-line. That is pretty much a 1-line that shows all the phasing and sometimes, in this case, the equipment for current circuits and voltage circuits as well. The DC schematic you see in the middle left is usually what is involved in the relay functional diagrams, where you'll look at your circuits and verify functionality. The middle right is the panel details. We also call these front views in some cases. This shows you the physical layout of the panel that you may be testing or any surrounding panels for all the relay equipment, test switches, lockout relays, etc., etc. And on the very far right is the relay logic diagrams. Those are always utilized for relay testing, understanding the functionality of some of the relay logic and how it should operate. Again, just going over kind of all the necessary equipment, drawings, everything. Adjacent systems, additional information to determine what else could be affected. So again, the lockout relays, for example. Let's see. So we're going to get into the outage and isolation plans. We need to identify for an outage what needs to be switched out of service. And what this means is when you take an outage at a substation, the client does not want to open up all the equipment and make the whole yard dead. Usually that involves them losing a lot of money, a lot of customers, and you're going to be putting more load also on other stations, other transmission lines, other distribution lines, etc., etc. So what they usually plan for when they initially design the substation is to allow multiple instances where you can open up maybe 2 or 3 or maybe even more breakers to isolate a specific portion of the substation without killing it altogether and allowing transmission lines and distribution lines to still feed and receive power. In our case, when we are asked to upgrade or test any equipment that is currently in service and will be put out of service temporarily, we need to identify that before we even show up on site. What necessary equipment needs to be operated, needs to be taken out without affecting anything that surrounds it. In this example, we're going to be taking an outage on the GCB BL2 breaker. Let's say the client wants us to replace some relays, replace those switches possibly, whatever the case may be. It's going to be important that we identify what needs to happen before we even start taking anything out. In this case, it would make the most sense to, first of all, open that breaker, open those switches on the left and right side, as well as opening the breaker on the opposite end of the Boston line. So I'm assuming that line runs to another substation, and at that station we should be opening that breaker to kill the line altogether, if that's what the client wants. Let's see. So in this portion of the slideshow, we're going to be going over some of the smaller equipment for example, the test switches, any of those little pieces of information contained within the schematics, and specifically in this case, understanding the order of operations for taking equipment out of service. So these are a few common examples of test switches. They are primarily used for isolation purposes, meaning that usually a relay that is in service will have wiring running out of the relay directly to test switches. This is primarily used for testing purposes, actually, not as much a safety example, other than something I'll discuss in a bit. But it's really useful for testing, because if the client wants a relay to be tested without any other equipment being taken out, it's very easy to, for one, isolate the relay just by utilizing the test switches. If we had to unwire all the contacts on the relay that were hot and isolate them that way, that could lead to a lot of dangerous situations, such as electric shock or misoperating of equipment. So the test switches are really nice. There's a lot of different styles of test switches. This top right FT test switch front is the most common that I've seen and utilized, as well as it's the easiest for relay testing purposes in general, because it allows you to connect that FT test paddle, which you see in the bottom left there. That's a test paddle that we utilize for relay testing that actually just plugs right into the front of the test switch block, and you can connect your wires from your relay test set to the block itself, and it makes it very easy to move them around for different tests and whatnot. We also, as I said before, the safety purposes for some of these test switches, as you can see on the bottom right of the test switch front, there are little tabs that are at the bottom, at the base. Those are primarily used for current circuits. I'm sure you guys haven't seen it firsthand, but opening a current circuit that is live is extremely dangerous and very bad for the current transformer itself. You never want an open CT. It causes damage to the current transformer. It will cause a misoperation on everything that surrounds that current transformer, and it could lead to disastrous on this end in the control house at the test switch front. So those test switches for the current circuits are utilized because at the bottom there are shorting blocks, meaning that if one of those gets opened accidentally and the circuit is still somehow hot and has current running on it, the block will cause a short and bring it directly to ground, and it may operate the breaker in this case, but it won't blow up the CT because the current circuit will still be completed. It'll just run directly to ground. So extremely useful, very much safer to utilize those rather than running them directly into the relay, for example, and a good tool to remember. So these are what the test switches look like on a DC circuit schematic. This is what we will look at when we're functionally testing the relay circuits. You can see they're identified by A, B, C, D, etc., as well as the numbers. The numbers indicate which side of the relay test switch should be going to where. Usually the odd numbers at the top will run directly to the relay, because it's more common than not that the relay will be installed above the test switches, as well as that's the easiest way to isolate them and understand that it's going to be isolated properly as well. We have multiple identifiers as well to the right here in the green circle. That is usually a client-specific identifier labeling the location on the panel itself. So in this case, we would assume and verify that it's going to be panel 2 in the AE spot, and as well as this is going to be test switch 6. As said previously, they identify them, the specific nice switches as well, A, B, C, D, and odd and even numbers. This is a example of an existing control house with all the relay equipment, all the test switches, and it seems like someone's doing some relay testing as well. So as I said before, it's really common for the clients to want the relays themselves installed above the test switches for sake of ease and safety precautions. We can see the table might be covering it up, but they're probably utilizing one of those paddles that I showed you earlier, and that's where you'll connect your wires from your test set, which is shown below to the right of the desk. Those plug in very easily. They're way better than having to screw in lug nuts to the back of the relays and plugging them in that way. It's simply just take the paddle, plug it into the test switches, and start testing. Relay testing can be a lot of fun until stuff goes wrong. Yeah, there's instances where you're just cruising along, you're getting good results, everything's lining up as it should, and then all of a sudden something fails and you have no idea why, because you followed the correct standards and testing values that you were received by the design engineers. So it can lead to a lot of troubleshooting, a lot of head scratching, head banging sometimes, but all in all, it's a pretty good gig, especially when it's -4 degrees outside and you're in the control house that's heated and everyone else is outside freezing. So this is an example of the AC-DC circuit switches. Usually for DC power to the relay, the clients more likely than not will run positive DC power to test switch A and negative DC power to test switch J. I think this is more or less a safety precaution and sake of ease for them, because you don't want that DC power to short in two different spots. If you were, say for example, you're going to put your positive on test switch A and your negative on test switch B. If someone were to accidentally put something metal across the top two terminals of A and B, that's going to create a short and ramp up the current and possibly destroy themselves or multiple pieces of equipment. So that's usually why they separate them from A to J. It creates the longest length possible for any shorting possibilities, as well as that's just kind of a standard that a lot of clients like to utilize. So up top, like I said, the switch identifier specifically is the letters, and they show you examples of the switches open and closed as well. This will dictate whether you have power running up to the relay or whatever circuit the switches are connected to or not. We have the example for the current switches as well. As I said, at the base of them, the shorting tabs, whether they are open or closed, if the test switch is open, as you can see on test switch D and E, the shorting pins push the shorting tabs down and create, like I said, create a short. As I said before, this is extremely important for current circuits because you never want to have an open CT circuit, or it could lead to disastrous consequences. But as shown in the middle F and G switches, when the test switch closes, it releases the shorting tab and opens the circuit up, allowing the current to not go directly to ground, and it'll just run up through the test switch up to wherever it's going. The pressing tabs are for security reasons. You want to make sure that those are in all the way and make a good connection. Otherwise, there's going to be heat that you can probably feel if there's a poor connection, and maybe a little bit of buzzing depending on how poor the connection is. With AC power, if you're putting a relay into service and that happens, the relay is going to see funky current readings and probably operate whatever breaker it needs to, and could run into problems there. We got an example of a 3-line that I discussed earlier, and the current switches that connect to this breaker's CTs. So you always look at the breaker CTs based on the polarity as well as what the ratio should be per the relay design. The polarity, you can tell, is the square boxes on the CT itself that will run directly from the field into the control house and go into a current knife switch. That will then go into, whether it's a relay or a meter, come out of it, go back into the knife switch, and then either loop back around to the neutral of the CT or to another piece of equipment if necessary. The line shown above each of the current knife switches is pretty much the shorting block that we discussed earlier in a schematic sense. It shows that the knife switches should have shorting block capabilities, especially for the CT circuits. So where we start when we're reviewing prints usually is with DC schematics. That's where we'll find details that we haven't seen in one line, since one line is just the bigger picture usually. DC schematics are the nitty-gritty ins and outs of all the protection equipment, any other equipment that may be in the control house, or even in equipment cabinets out in the yard, such as breakers or CCVTs, which are capacitive coupling voltage transformers. Usually, there's not really a best place to start reviewing, depending on the project, in my opinion. If it's a greenfield and nothing's in service, you can really start wherever. Usually try to start with, like they said, DC schematics. Verify that all the equipment is there, properly hooked up, the wires are in the correct place before you even turn anything on, any power to the equipment. And then make sure you make a list and highlight as you go along. When you're verifying the equipment, you don't want someone else to go back and recheck stuff. That's a waste of time, as well as you could miss stuff in that process. So marking up the prints, verifying point-to-points, and when you functionally test, highlighting as well. It saves you in the end and verifies that the equipment was tested properly. We got another example of a DC schematic here. What is circled right there is what they call the revision block. It pretty much gives all the information on this specific drawing, shows who the manufacturer was depending on what kind of drawing, if it's a breaker or something like that. It gives you the rev numbers, so making sure that you have the most up-to-date revision of the drawing is extremely important. When it was, who designed it, any reference drawings that may be associated with it, as well as identifying the equipment, which will be shown right at the bottom right there. So in this case, we have a DC relay schematic that identifies the correct piece of equipment that we're going to be testing. Up in the top left, we have a communication board. This is a CL411L communication board. That's interesting. I've never seen one of those before. It is pretty much a piece of equipment that allows comms between one relay to another. In this case, it's going to be a 411L that connects to what would most likely be another 411L, whether it's at the site, but usually it's going to be somewhere else entirely on a transmission line, at the end of the transmission line. It could be connected through fiber optic cable, which is usually the most common in this day and age. It's not super expensive, it's extremely reliable, and it is extremely fast communication. There's also Ethernet, which could be utilized depending on the situation, and serial, which is very, very, very project specific. To the left of the schematic, we have the DC circuit power supply. This is what you do before you even turn anything on. You verify the power supply is the correct voltage for one. You got to see what the relay is rated for. In this case, you verify the relay is rated for 125 volts DC. You verified in the schematics that you're going to be receiving 125 volts DC, and then you will go and verify that it is in fact 125 volts DC at the breaker cabinet before you even turn anything on. You'll measure it, verify it, and then you'll hook it up and put power to the relay. To the right, these circles is pretty much continuations. So if this drawing can't fit all the equipment that may be on the DC circuit, this circuit specifically, they'll just reference to another drawing so that you know this power supply to the left will not only feed this relay but possibly something else on a different drawing. It's extremely important to catch those and verify the other equipment is rated for 125 volts DC as well before you turn it on. On this relay specifically, what's squared off here in red are the relay outputs. These are usually what will send signals to operate the high voltage equipment, such as the breakers, any other reclose, initiates, as well as the relay failure alarms. The relay failure alarms are usually communication points that go to other relay inputs and will notify them, especially if this relay fails. If it bugs out, just shits the bed at all, it will send a signal that the relay failed to another relay, for example, and that will be sent to dispatch to notify them. The green box is all the relay inputs. Those are the signals that you're going to be receiving from either other relays or even the high voltage equipment itself. You can see in the left of this green box there's a 52.1A contact. That is a breaker contact that indicates whether the breaker is open or closed, and that's what we'll be utilizing to monitor the breaker that's in the relay circuit. As well as general notes. Usually it's just stuff that you want to make sure that people look out for if they're doing any testing or if they're going to be operating any of these pieces of equipment. So we got a little zoomed in picture of the relay schematic. We got the identifier, which is that top left circle right there. We know it's going to be in panel 2 in position AC, and as well as the unique identifier. The unique identifier is very client dependent. Everyone has a different way of identifying their equipment, whether it's kept track by the relay type. For this example, you could almost assume that it's going to be a 421 for this case, based on that, but it's actually a 411L because it's going to be a line relay code, as well as B2, which could stand for backup or backup 2, for example. You should understand which client you're working for, understand their standards and the way they name a certain piece of equipment, and it'll help you in the process when you're troubleshooting, especially. Again, more unique identifiers for the relay test switches here. We got panel 2, position AD, and it's going to be test switch number 3. They do unique identifiers for terminal blocks as well. Terminal blocks are on the side of the panels in the relay cabinets that are pretty much a junction point for cables that will come into the cabinet from another panel, a breaker cabinet from outside somewhere. Terminal blocks are usually the first thing that the cable will hit before it even touches even the knife switches, for example. Again, unique identifiers, panel 2, terminal block is usually TB, and position 3 on the terminal block. We also have unique identifiers for terminal blocks that are not in the cabinet. The one below 2TC-2 will be in this cabinet. It's going to be marked panel 2, but you can see that again it actually has cabling leaving the cabinet and going to another panel, for example. It's actually going to be going to panel 5, and you can also identify that with the little cable number that runs in between those two circles, 86BL2-2ST. That little loop is pretty much just indicating that this isn't just a wire that's in the cabinet. It's a specific identifier for a cable that may be leaving or coming back in. As I said before, that 52-1 is a breaker contact. That is going to be identifying whether the breaker is open or closed, which is extremely important for the relay to see, to know when to operate and when to not. You don't want it to keep opening a breaker that's already open. That's just silly and doesn't make any sense. And you definitely don't want it closing in when it's already closed in. That's what we call an anti-pump, which I can just glance over very briefly. An anti-pump scheme is a safety protocol for breaker failure situations. Pretty much what happens is, if the circuit isn't hooked up a certain way, the breaker could close in and then continuously keep trying to close in. The reason why that's an issue is the way the breaker closes is run by a motor. So if that motor keeps firing off, and these motors are rated for, they put out like sometimes like hundreds of amps at a time just to operate the breaker, just to close it. So if that closing mechanism keeps occurring, it keeps popping out hundreds and hundreds and hundreds of amps over and over and over again, that's going to heat up and eventually fail to the point where the breaker will it'll just be a pile of junk and it won't work anymore. So like I said, the anti-pump scheme is a protocol that we use to hook up the wiring a certain way so that you can only close a breaker once unless it's a reclose initiate scheme, which is an entirely different set of contacts that will come in. It's a lot of interesting stuff that you learn out in the field, stuff that you won't really ever get to know in an office setting, for example. You'll definitely, in my opinion, I think you'll understand how like the power equipment functions a lot easier when you see it in a hands-on situation. I've also found that the design side you can learn quite a bit as well, but seeing it firsthand and I guess playing with it isn't the right word, but I guess, yeah, playing with it a little bit and getting a better understanding is super beneficial in my opinion. So, and you learn a lot of cool stuff out there. 52 is always going to be the circuit breaker identifier. It's labeled 52 everywhere I've seen. Another example for the naming conventions, 5HA, that's going to be in panel 5, and those two open contacts that run in series together, that is usually a lockout identifier, lockout contact identifier. And like I said, lockout relay. Wiring diagrams, they look completely different than schematics. Wiring diagrams are usually what the electricians will go off of when they're putting the panel wiring together. They identify where the equipment's going to be specifically in the panel, identify all the naming conventions for all the terminal blocks, relays, test switches, lockouts, etc., etc. And it should be a fairly good physical representation of what the panel should look like. Again, red blocks identifying the drawing, which cabinet and job numbers, etc. So you're always going to be looking at the back side of the panel when you're looking at a wiring diagram. The back of the panel is where you access all the nodes to all the relays, all the backs of the test switches, and where you'll access the terminal blocks. At the front of the panel, you can see the front face of the relay, the actual knives to the knife switches, and then the mechanical operative pieces of the lockout relays and whatever else may be in there. But the terminal blocks usually you can only get to in the back of the panels, and that's usually because there's no real operation to begin with. It's just a junction point for wiring to enter and exit. So when we're looking at a wiring diagram, always be aware that you're going to be looking at it based on the back of the panel. So if you're looking at the back of the panel, the terminal blocks to the right will be on the right side, and that's for example. When you're looking at the terminal blocks, depending on which side you're on, this is very important, but it will determine whether you have external or internal wiring. For example, where we have circled here, it's going to be on the left side of the panel, meaning that the outermost parts will always be the external wiring that's coming in or leaving, going to another cabinet, and anything on the insides of those terminal blocks is what's just in this panel, for example. This is a disgusting example of the back of some panels. This is I guess what you'd call an open concept. I see a lot wrong with this. There's a lot of hazards associated with this. Somebody's got a coffee cup on one of the relays. That's always good. Excuse me. A lot of times you won't see it exactly lined up like this. Usually the cabinets are an enclosed space that is only designated to the equipment associated with the panel. So we got the comparison actually now between the wiring diagram and the DC schematic. We can this is always a good check as well to verify that the wiring matches what you have on the functional circuits. So whatever the electrician's installed matches what you are going to be testing, pretty much. So the first step, you definitely want to identify you're in the right panel, identify the equipment that you're going to be checking, verifying, making sure it's going to the right places. So this quick little example, we identify the test switch. We'll be connecting to the power source for the relay. You're verifying that Z30 goes to B3 in this case. You'll physically check that as well to verify that that is the case. And that way you know that everything matches up. You also want to identify in the wiring diagram that the naming conventions are correct, depending on which piece of equipment you're looking at. So we're going to go over a quick little process for the isolation procedures. Again, we're going to be looking at our zones of protection, identifying what equipment is going to be necessary for the isolation, etc., etc. We're pointing out the CCBT fuses here that show the voltages that are going into the existing relays, as well as the 3-line schematic for the voltages as well. The process for isolation, you definitely want to identify your current and voltage sources first and understand that they are coming from the correct piece of equipment to the correct relays that you're going to be isolating. That's what we're doing here. And there's a order of operations for the process of isolation of equipment. For example, let's say we're taking a relay out of commission for however long. The relay test switches will be opened in a specific order, and that is because you want to avoid having anything in that could operate a piece of equipment that you do not plan on taking out of service. For example, first of all, you want to verify that your outage request is fulfilled and you can start the procedure. Get the okay from the client or utility. Your first thing you want to isolate from the relay is the trip paths. And the reason you do this first is because the trip paths are all outputs from the relays, meaning it doesn't see anything. The relay won't see anything if you take away its trip path. And the reason you take these out first as well is because if you were to take out any of the currents or inputs that are going into the relay may think something's wrong and will trip that equipment associated with the trip path. So you take those out first. Test mode as well, any communication paths, DC power to the relay if need be, and then your last leg is going to be your current and voltage sources. Order restoration, to put the relay back into service, pretty much just go complete opposite way. You start with the currents and voltages, power up the relay. Always check the relay for any standing trips, meaning once you put power into the relay, you look at it, you see if anything's wrong before you put those DC trip paths back in. If you put one of those DC trip paths back in and there's a standing trip on that relay, it will immediately operate that piece of equipment and cause another outage that you did not plan on. and the client does not like that. So each time you put something in, you look at the relay, verify that there's no standing trips, there's no issues with the relay, and then you continue on in the correct order of operations in this case. Once that is completed, you communicate with the client that the relay has been restored, your outage request has been fulfilled, and the equipment has been returned into service, meaning that there is nothing else to do other than cross your T's and dot your I's on your documentation and submit that and get out. The relay is back into service and the substation is good to go. So that's all I have for this class specifically. Again, if you guys have any questions, please feel free to reach out using the email or the phone number that I had in the second slide of this presentation. So thank you all for your time, and I hope you guys have a great day.